All right. A couple of things. One, we talked about, I sent an email out to everybody yesterday, I think. Yeah, that had this. So what I call the home stretch schedule. We're in the last sort of handful of weeks of the class. And this is kind of the schedule for the rest of the semester. So what we're going to talk about on each day, what sections of the textbook they come from, if there's a self-study assignment. We will dip into Unit 13 just a little bit, but there will not be a self-study assignment for Unit 13. Let's see what else is there. Yeah, so you got a Verilog project tonight, or today. That starts today. It's due next Monday. We'll talk about that in a second. The next exam is going to be at some point, November the 23rd. It'll be a 50-minute timed exam on Blackboard. It's going to be multiple choice, 65 multiple choice questions covering units 11, or everything that we've talked about from today through the 18th. And also on that Friday before, we'll have a review session for that midterm exam. And then on December the 4th, and this is true regardless of what the final exam schedule says for your specific section, all of our sections 1, 2, and 5 are going to have our final exam on Blackboard on December the 4th. It'll be 100 minutes, 130 questions, same deal, multiple choice. However, it's optional, and it will replace your lowest midterm exam grade. So if you, and there's no risk to taking it, right? So especially since it gets graded automatically because it's multiple choice, like it doesn't require any extra work from us to grade it. You can sort of take a crack at it, and if that's your lowest grade, then that will be dropped. So there's no inherent risk in taking the final exam. We'll do 2 reviews when we get back from Thanksgiving. We'll do a review on Monday of units 1 through 5, and then a review on that Wednesday of 7 through 9, and then that Friday will be the final exam. So are there any questions about the schedule for the rest of the semester or the format of the exams?
When, like, for exam 3, it says 65 questions. Is it like 65 questions that we can do in a lot of time, or was it just meant to flood out so people don't have time to cheat?
Yes. So I read some articles on how to minimize cheating on an online test, and one of the high points was a sort of fast-paced exam. So that's 65 questions in 50 minutes. That shakes out to roughly 45 seconds per question, which means basically, the premise there is you got to get to the question. You got to know if you either know the answer to the question, maybe there's a little bit of calculation, but not really. There's no time to look up the answers. You got to actually know the answers to the questions. And now what that means is the individual questions themselves will be a lot easier than the ones you've seen in the past, right? But you still got to have, study the material and know what you're talking about. And I've done a lecture in PowerPoint, and I'll use that moving forward. We'll kind of see. I'm trying to create as much resources as you can to study for a multiple choice test. But I know I said a lot. But 65 questions, 50 minutes, approximately 45 seconds per question. Any other questions about the exam?
Will there be a lot of theoretical questions?
Will there be a lot of theoretical questions? Can you be more specific? What do you mean by a theoretical question?
For example, like something from the textbook, I cannot come up with something right now, but you need to read the textbook in order to answer the questions, not calculation questions.
Yes, I see what you're saying. Yes, absolutely. You will need to read the textbook. There will be, in fact, we'll even talk about it in today's lecture. There will be sort of vocabulary words that you need to have memorized and know those definitions and stuff like that. So yes, you'll need to read the textbook. So I guess you could say it will be all theoretical questions. From the lecture and then from the material in the textbook. So for example, make sure that you have read and studied, sections 11.2 and 11.3 from today, as well as looking at the paying attention to today's lecture. And I'll also post the lecture slides on Blackboard. Esteban, there's always the same curve is there as always, right? I mean, there's no curve on the exam itself, but the curve happens at the end of the semester. All right, any other questions about that? Okay, in that case, the other thing we need to go over is I assigned your first project. It's going to be right here in this HDL projects tab. It's due 1 week from today. The title here is Combinational Logic Design. And let's take a look at the description here. Zoom in a little bit. A couple of things. Submission instructions. When you're done, you're going to turn in just one .v file. So you don't need to turn, if you did your own test benches or anything like that, you don't need to include any of that. Just one .v Verilog file that's named this, your last name underscore your first name .v, and then inside the, well, we'll get to it in just a second, right? So you're going to turn in on Blackboard just your Verilog file. We have our own test bench that we run that will do the grading for you. Here's the description. Implement a Verilog module to realize a logic circuit to the following specifications. Take as data inputs two 4-bit 2's complement binary numbers, which means these are numbers that can be positive or negative using the 2's complement method, A and B, as well as a single 1-bit control input C and a single 4-bit output Y, which is also 2's complement binary number. And the value of Y should be equal to the sum A plus B if C equals 0, and the difference A minus B if C equals 1. You'll be given a test bench file to verify your results, and you don't need to worry about overflow conditions, right? Just let the overflows happen. And then if you don't like the sort of word problem version here, I also kind of laid everything out. Your module, even though you're going to name your Verilog module last name underscore, you're going to name your file last name underscore first name .v, I want you to call your module itself just top with these parameters, A, B, C, and Y. And the reason you're going to do that is in Verilog, top is used commonly, kind of like main is in other programming languages, like C++, right? The main program or the main function or whatever. Top is like the sort of Verilog version of main. So call it top. With that, two data inputs, each are 4 bits, A and B, a control input C, and then an output that's 4 bits that is equal to, if C is equal to 0, then Y is equal to A plus B, and if C is equal to 1, then Y is equal to A minus B. So, any questions about the project description here, or the submission instructions? Okay, now included with that is you're also going to get, let me open up VS Code real fast. Over here. Let me pull up. I've given you the test bench that we will use to grade your assignment. So let me show you what that looks like. So if you go here, you can see you've got project1 underscore tb.v. So here's what this test bench file looks like. And this is I've given this one to Max. This is the test bench file that Max is going to use to grade your assignments. The only thing you'll need to do is make sure you change this to your actual file name. And then it's just a regular test bench. And then just notice that we have a score parameter here. And then it does some checking, and then at the end, it just says final results D of D. So the circuit has 9 total inputs, which means that there are 512 test cases. And basically, you gotta pass all the test cases. The way Max is going to grade it is if your file doesn't run. So if the test bench crashes or it throws errors or something during any part of the process, then you will get a 50. If it runs, like the simulation runs, but it fails all of the test cases, you'll get a 70. Or if it fails most of the test cases, you'll get a 70. If it runs and passes most but not all of the test cases, you'll get an 80. Or an 85, excuse me. And then if it passes all the test cases, you get 100. So those are really the only, there's not a lot of granularity in the grading for these projects. And really it comes down to either it works and you got 100 or it didn't and you got a 50. There's not going to be a lot of in between. But yeah, so there's no excuse because like I said, because you've been given the test bench here, there's really no excuse for anyone to get a 50 at least. Everyone should get at least a 70, even if you could turn in an empty module and get a 70. So, any questions about the project? Cody asks, so are we graded in terms of how many test cases we pass? Yes, but there's two caveats to that. One, you're graded on did you pass all, most, or, not most of the test cases. And the reality is, yeah, so if they're all successful, then the project is successful. It's been my experience that there's usually not a lot of granularity, right? Students' submissions usually either pass all the test cases or they pass none of the test cases. And there's very rarely any sort of in-between. Do we still get extra credit for demonstrating the projects on actual hardware? Was that ever going to be a thing? Oh, if it's on the syllabus, then it's on the syllabus, yeah. But I don't remember. It's been like a lifetime since then. Colbin asks, will we be getting the test benches on the other projects later? Yes, when you get assigned the other projects, you'll get those test benches. All right, any other questions about the project? Esteban is typing. Esteban asks, so we get those test benches and all we need to do is modify them? No, you should not modify the test benches. You have to write your own module that runs on the test bench. The test bench, you should not change the test bench, except for the only thing you should change in the test bench is changing this very first line to include to be your actual file name. That's the only thing you should change. Everything else you should leave exactly the same. Then you write your code, and this test bench will test your code.
We are uploading it on a Blackboard, right?
Yes.
Oh, okay. If we accidentally save it as just like project one instead of first name and last name, would there be any penalty for that?
Yeah, I'll give you a 0.
Dang.
Savage. Don't do it, man. First name, last name. It's easy. We'll call that the first part. You can follow the basic instructions. And if you can't do that, then yeah, you're going to get a 0. So name your file correctly.
I was wondering because I don't know if I had to change the bat file or not.
Oh, the bat file. What did you name the bat file? Or what's it called in the bat file? I mean, that's your own thing, so just mess with that on your own.
Yeah, the bat file just assumes that the regular one and the test bench are the same name, except for one has underscore test bench, and that's why I was wondering.
So, I mean, I think that the clever thing there is once you have the test bench, you can do whatever you want, right? The only thing you need to make sure you do is before you submit it on Blackboard, change the file name to be last name underscore first name. Does that make sense?
Yeah.
You can change the file names to be whatever you want while you're working on it yourself. The only thing, and remember, you're not going to turn in the test bench. You're just going to turn in your file. So as long as you name the file before you submit it, then that's all good. All right, anything else? Before we need to have class now. All right. So enough of that. We're going to go with PowerPoint slides today. I did that in my 3304 class on Friday. That seemed to work really well. So we're gonna do that. Also, I'm going to upload these. I'll do it right after class. I'll upload these slides to Blackboard. That way you've got some reference, including, such as down here at the bottom, I've included like a list of the important sort of definitions you need to know, right? These are really, these make for really easy multiple choice questions. So they're definitely going to be on the test. So make sure you go and look over these terms and kind of memorize what they are. Gives you good context to sort of build on what we're working on. So let's go ahead and do the thing. So we are in Unit 11 now. Specifically, we're doing sections 2 and 3. 11.1 is just an introduction, and I think we actually do cover 11.1 here, sort of briefly, but it's just some introductory stuff. So we're going to talk about SR and gated latches. Our objective today is in this lesson, we're going to characterize the operation of what's called the latch circuit by deriving its characteristic equation. And we'll talk about what a characteristic equation is here in just a little bit. I'm told I talk really fast, especially when I do PowerPoint presentations, so I'm going to work on speaking slowly and not just clicking through the slides really fast. If I go too quickly, say something or sort of speak up, and I'll sort of work on being a little bit slower. So the overview of today's lesson, we're going to talk about first feedback in switching circuits, set reset latches, deriving the characteristic equation, probably the most important part of this lecture, and gated latches. Let me go back fast. And we'll talk about the difference between a set reset latch and a gated latch. So first, let's talk about feedback in switching circuits. So a sequential switching circuit, here's the definition. Sequential circuit is a switching circuit, right? Remember, a switching circuit is just, any logic circuit, any circuit that consists of gates, in which the output not only depends on the present input, but also on the past sequence of inputs. So up until now, we've been doing what's called combinational logic, which is you have a circuit, you give it inputs, and it spits out outputs, and everything happens relatively instantaneously. There's no memory in the circuit at all. So these circuits need to be able to remember the history of inputs to produce the present output. So it's not just the, not just the inputs to the logic circuit, but also some history, some past, what we're going to call state. So we need to, in order to implement those types of circuits, we need to create memory devices that can have memory, that can store state even when the inputs change. And that's the topic of today's lecture and on Wednesday's lecture. Latches and flip-flops are the primary circuit elements that have memory. They can store state. So, latches and flip-flops. Latches and flip-flops are commonly used memory devices, and they can assume one of two stable output states from multiple inputs. Remember, we're still working with binary numbers. Here, actually, I'm going to do a thing real fast. I'm going to exit out of this. I actually want that prisoner view. I need you to come over here so I can actually see what's going on next. Okay. Latches and flip-flops are commonly used memory devices, and they can assume one of two stable output states from multiple inputs. So at the end of the day, we're still storing bits, right? A latch or a flip-flop still can only store a 1 or a 0. They're 1-bit memory devices. So even if there's multiple inputs to a latch or a flip-flop, at the end of the day, the goal is just to store a single bit. So that's why we say they can assume one of two stable output states from multiple inputs. So let's take a look at a really simple example of a memory circuit. What might happen if we connect the output of an inverter to its input? And what I mean by that is if we built a circuit that was this. We had a simple inverter with the Boolean variable x, and if we just took the output and directly tied it around to its input. Take a moment and kind of think about what do you think would happen in that case? What would the behavior of this circuit look like? Anyone want to offer a guess?
Would it just flip back and forth between 1 and 0 constantly unless another signal is inputted?
Yeah, absolutely. Very good. Right? And in fact, even in this circuit, there is no other input. So you can imagine we power the thing on, it's in a 0 or a 1, and it's going to constantly sort of cycle through.
Could it be thought of as a clock?
Ooh, yeah. We're going to get to that, but you really sort of hit the nail on the head, man. In fact, we're going to refer to this type of circuit as a clock, but we're going to come back around to it. So the first definition we need is feedback. Feedback is going to come up a lot. Yeah, and in fact, redstone clocks in Minecraft are based pretty much entirely on this concept. So a definition here, feedback. Feedback happens all of the time. Feedback is actually a sort of fundamental construct of sequential logic circuits. And here our definition is when the output of one gate is connected back into the input of another gate in the circuit in order to form a closed loop. So when we have output of a circuit that feeds back around to the input, we call that feedback, and that's sort of the center of a sequential logic circuit. So keeping it going, let's kind of math this out, right? So if we choose 1 or 0 to be the present state of the inverter, it doesn't matter what we choose. So let's just say it's equal to 0, right? After some propagation delay, that 0 arrives back around on the input, and then the inverter switches to 1. And then after some propagation delay, the 1 arrives back around at the input, and the inverter switches to 0. And this process will continue forever and forever and forever, right? We're always going to be going back to 1 and 0. So if we were to draw the timing diagram for this circuit, it would look like this, right? This sort of constant oscillation between 1, 0, and 1, and 0, and 1, and 0, and 1, where the duration here is defined by the propagation delay of the inverter. So whatever the propagation delay of the inverter is, that'll be the width of these halves of the pulses. Another definition here, an oscillator is a circuit which continuously toggles between states, right, where it does it automatically, right? We can manually make circuits toggle between states by providing inputs, but an oscillator circuit will specifically on its own, if you just take your hands off, will on its own toggle between different states. Any questions about this example? Right, we had an inverter with a simple feedback loop tying the output of the inverter back to its input, and we see here that it just oscillates between 0 and 1 automatically, which makes intuitive sense when you think about how an inverter works. An oscillator also has what's called an unstable state, but before we can talk about an unstable state, we need to know what a stable state is. And our definition here, a stable state is when the feedback provides a signal which will not result in a change of state, right? That inverting oscillator is inherently unstable, right? Because no matter what state you put the output in, it is always going to change the state, right? 0 is always going to become a 1. A 1 is always going to become a 0, and so on and so forth. But for a circuit to be in a stable state, the output needs to be something that will not change when it comes back around to the input. So if it stays in one place, if it's a 0 or a 1, then it's considered to be stable. A really basic example would be something like this. If we put two inverters in series and connected them, right? If you put a 0 on the input, you're going to get a 1, and then a 1 is going to convert it back to a 0, right? And the 0 propagates around, and we still have a 0 on the input of the inverter, right? So the state will never change. So this circuit is in a stable state. Obviously, this isn't a very interesting circuit, and it doesn't really do anything useful, but it is stable. The output will never change based on when it comes back around. Same thing for this one. If we put a 1, 1 becomes 0, the 0 goes to the next inverter, becomes a 1 again, and we have a 1 that passes back around. So while this is a boring circuit, it is a stable circuit. Could you make an oscillator of 3 inverters? Yeah, that would be an unstable state, right? And instability is what we want for an oscillator, right? So if we had 3 inverters in series, it would go 0 to 1, 1 to 0, 0 to 1, right? Which would be inverse, and it would flip back around, right? So if you have an odd number of inverters, you'll get an oscillating circuit. So if you need to change the sort of width, the frequency of your oscillations, right? You can just sort of stack inverters in series, so long as you're always adding an odd number of inverters. All right. Any questions about this sort of inverting feedback concept? Okay. So now let's talk about set-reset latches. This is kind of what we want to get into. So a set-reset latch is the same concept that we just looked at for the inverter, but instead we can construct a simple latch by introducing feedback into a 2-level NOR gate circuit. So a circuit that looks like this. We have 2 NOR gates connected in series, and we've got some labels for these nodes, right? We have an S on this first one, an R on the second input, or the input to the second NOR gate. This output of the first NOR gate we call P. It's tied to the second NOR gate, and that output is called Q. Oftentimes we're going to use Q to represent the output of a sequential circuit, and then sometimes or Q to represent the state of a sequential circuit, excuse me. And then the output Q is fed all the way back around to the input as a feedback loop to the input of this circuit. So the first question we need to ask is this circuit stable in its current state? So if we have a 0 and a 0 on the input, all right, it's a NOR gate circuit, so let's see, we have a 0 on the output, that comes back around, so we have 0, 0 on the NOR gate, means we're going to have a 1 on the output of this NOR gate, so we have a 1, 0 on the second NOR gate, which gives us a 0 on the output of the second NOR gate. No, so Cody asks, are R and S ground? No, they're the inputs to the circuit. So they're external signals that we're putting into the circuit. We'll set R and S to be different values to get different types of behavior. But here we're just saying if we start with 0 and 0, we get a 1 and a 0 on an output. So P stays at 1. Yeah, they don't have to be 0. In fact, that's the whole point, is that we're going to change them and take a look and see what happens to this circuit. So with S and R both equal to 0, the circuit is in a stable state. The output Q is always 0, and it's going to stay that way forever. But what happens if we sort of toggle the inputs S and R, if we mess around with this latch? So the first thing we want to do is say, well, what about, S equals 1 and R equals 0? What happens here is, so if we have a 1 on the input to the NOR gate, remember that, X, what did we talk about a long time ago, right? X, well, never mind. Anytime we put a 1 into an OR gate, we're going to get a 1 on the output, which means anytime we put a 1 on the input to a NOR gate, it doesn't matter what the other input is. We're going to get a 0 on the output P. Now we have a 0 and a 0, which gives us a 1. Q1 comes back around, and we have 1 and 1, which is still 0 in the output P, which means that the circuit is going to stay in this stable state. So when we set S equal to 1, the output Q, the Q output, will be stable at 1. Any questions about how we get a 1 on the output of this? This is the important part. Okay, so next what we want to do is, what happens if we had S equals 1, R equals 0, gives us Q equals 1. What happens if we now put S back to 0? Remember that 1 is still on Q, so on the input of this first NOR gate, we have 1 and 0, which means that P is equal to 0, and 0, 0 gets us 1. So when we bring S back to 1, or excuse me, back to 0, Q stays at 1. It stays in the 1 state. This is sort of the essence of the memory aspect of a latch. All right, we put S equals 1, Q into 1, and we return to 0, 0, but Q stayed at 1. Now we're going to turn around and flip R to 1. And what happens here is, remember, we put a 1 on the input of a NOR gate. We're going to get a 0 regardless of the other input. So R goes to 1, Q goes to 0. Now we have 0, 0, which gives us a 1. 1 and 1 gets us 0 on the output. So when we put R equal to 1, our output Q goes to 0, and it stays there. So with R equals 1 and S equals 0, Q output becomes 0 and is stable at 0. Now finally, if we bring it back to S equals 0 and R equals 0, from Q equals 0, now we're kind of back in that initial state, right? The output Q was 0, 0, 0 gets us 1, 1 on the input of the second NOR gate gets us 0, so it stays Q equals 0. So the sort of crux of the behavior there is, our inputs are S and R. If S goes to 1, then Q goes to 1, and if we go back to 0, it all stays the same until we say R equals 1, and then Q goes to 0, and then we go back to 0, and Q will stay the same. So Q will remember whatever the inputs of S and R were after they've gone back to 0. Oftentimes we refer to S as the set and R as the reset, and basically that just means as the set, when set goes to 1, state goes to 1, and when reset goes to 1, state goes to 0. Are there any questions about that behavior? All right. Now we showed the S-R latch in this sort of feedback form because it fits really nicely with the example that we used with the inverters. But oftentimes you're going to see a set reset latch drawn in what's called cross-coupled form. So latches are often drawn as cross-coupled with a Q and a Q prime output. So a circuit that looks like this. So we still have our two NOR gates, and it's fundamentally the same. So we have R, set into that first one. It comes back around into the second NOR gate with R and Q, but we add this second feedback loop so we can get a Q prime output. And these will always be the inverse of each other. So if Q is 1, Q prime will also always be 0. And if Q prime is 1, then Q will also be 0. They'll always be the complements of each other. And if you don't want to draw the NOR gates, oftentimes you'll see it just as a box drawn with a little L there, and R and S on the inputs. So like I said, this is the cross-coupled form of an S-R latch. Now we talked about this sort of state when we have S equals 1, R equals 0 makes Q equal 1. When R and S are both 0, state doesn't change. When R equals 1 and S equals 0, then Q goes to 0, and then we go back to 0 and S doesn't change. That leaves one more possibility that we haven't considered. And it turns out it is possible to sort of break a latch. There's an improper case, right? We call it improper latch operation. The case when S equals R equals 1 should never be allowed. And it leads to what we call unpredictable behavior. When we set S and R both equal to 1, then it's going to do something, right? By the sheer physics of the circuit, it's going to fall in one state or the other, but it becomes unpredictable. There's no way to know what's going to happen. So for example, if we were to look at it this way, where we had, S, and we tied it to, now they've named the outputs P and Q. If they're both equal to 1, and then we both set them at 0, then actually what happens is the circuit will start to oscillate. So if we go from all 1s to all 0s, when we're at all 1s, we get all 0s on the output. Remember that the outputs of our cross-coupled latch have to be inverses of each other, so this is a bad case. And if we go to 0, assuming that the NOR gates have the same propagation delay, they'll go from 0 to 1 to 0 to 1 to 0 to 1. So the take-home message there is, never let S and R both equal 1 for an S-R latch, and if you do, it can lead to some unpredictable behavior, including it can cause the S-R latch to start to oscillate, to start to have both of its inputs go 0, 1, 0, 1, 0, 1, 0, 1 forever, which is bad, right? Especially, you never want a circuit that's supposed to be just storing a single bit to start oscillating. All kinds of bad stuff can happen. Any questions about this?
If it's an unpredictable behavior, could it not be used as a random number generator?
Ooh, that's a good question. You could actually, yeah. I mean, you'd have to have multiple ones, but the problem is it won't always do that. Unpredictable also means sort of unpredictable, right? A random number generator, if it starts to oscillate, then that's not a great random number generator, unless you want to generate a sort of series of random numbers.
It could just be for the seed, like, because a lot of the pseudo-random numbers make a seed, and they could just say, okay, I want to make a seed for a random number, so it just does this, have a certain amount of time go by, and then samples whatever the value is at that moment, and then use that as the seed.
That's a really good point. I never thought about that before. But yeah, you could load them up with zeros, or load them up with ones, and then sort of see what state they fall in. You'd have to sort of like be paying attention and catch it before it oscillates. So I don't know if people will do this in practice, but it might actually be kind of interesting to get some S-R latch integrated circuits and sort of test them in the lab. That'd be kind of an interesting experiment. Michael asks, how do S and R change to 0? Well, remember that the sort of Boolean expression for our NOR gate says that whenever one of the inputs to the NOR gate is 1, the output will be 0. So in this case, when we have 1 and 1, that means we're going to get 0 and 1 on the outputs. But what happens is, I need to figure out how to, there's a way to like draw on this, but I don't know how to do it off the top of my head. So when S and R are both 1, we're going to have 0 and 0, right? So it'll be arguably stable at 0 and 0 until you flip them over, right? So what happens then is you have, when you go to 0, you have 0 and 0 and 0, which means that you have all zeros on the inputs, which means that these click over to all 1s. And then if you click them back over to 1s, now you have 1, 0, so it goes back to 0. So you can see where it starts to sort of flip-flop back and forth between 0 and 1. Did that answer your question, Michael? Your original question was how do S and R... Wait, I think I misinterpreted your question. You said, how do S and R change to 0? Remember, these are inputs to the circuit. So we set them as 1 and we set them as 0. Or whatever we're doing on the outside sets them to 0. Yeah, we just choose them, right? They're inputs just like any other inputs that we've talked about before in this class. Sorry, I thought you were talking about how does it make them all be zeros, but your question was simpler than that. All right, any other questions about this behavior? So now I'm really thinking it really would work as a random number generator because this oscillation assumes that all the timing is exactly the same, which won't be the case, right? One will, just by sheer physics, one will happen before the other, right? The odds of them happening at the same time is pretty unlikely. So it will fall into one state, but which state it falls into is sort of random. I really kind of want to do this experiment now. Maybe that'll be a project for students next semester. Okay, let's move on. Let's take a look at a timing diagram for the S-R latch. And there are a couple of important things to note here, right? So we've got our S input, we've got our R output, and we've got our S input, R input, and our Q output. Most of the time we only concern ourselves with Q. We don't really worry about Q prime or the P. We're only worried about the state of our latch. So if S and R are both 0 and Q starts at 0, it's going to stay at 0 until S goes to 1. And then there will be some propagation delay, right? Some tiny amount of time, right? So if at T equal T1, S goes to 1, some itty bitty delay, which we use epsilon to represent here, will pass before Q triggers, and then it will stay until, remember, S goes to 0, and the output stays at 1, right? It's going to remember that state until it gets the new state, right? And that comes from the R input toggling. So at T3, R goes to 1, and so that same amount of delay, that same epsilon time will go, and then Q will drop back to 0, and then if R goes back to 0, excuse me, then Q will stay at 0. The important thing here is the duration, right? The duration of the state change in S must be greater than or equal to the propagation delay in Q output, which basically means if you were to toggle S faster than this time epsilon, then the state will never change, right? You have to at least be 1 for this entire duration of time for the state to change and Q to go to the next state. Which when we're running circuits that are really fast, running at gigahertz speeds, right, this sort of things matter. We don't want to clock faster than the state can update. So we have to be aware of how fast our memory can update when we're sort of thinking about our clock speeds and stuff like that. All right, any questions about the timing diagram? Big take-homes here are just, when S goes to 1, Q goes to 1, and then it goes back to 0, it stays, and then when R goes to 1, Q goes to 0, and then it stays. And then we got to make sure that whatever our pulse that we use to change the state has to be longer than the delay in the Q output. If we don't do that, it leads to what we call a metastable state. So we have stable, we have unstable. Metastable is when the voltage level at the output of the circuit is approximately halfway between the voltage levels for a logic 1 and a logic 0, right? If I go back to our timing diagram, right, we sort of draw it as happening instantaneously, but we've already talked about the fact that it's not quite instantaneous. And so during this time when it's sort of in between, right, anything could happen. It could start triggering, it could stop triggering, like you could not trigger. It's what we call metastable. And there are several cases that you need to be aware of that can lead to a metastable state. The first one is a simultaneously switch from 1 to 0 in SNR. This is the one we already talked about that can cause it to oscillate and cause all kinds of weird stuff to happen. So when we have SNR at 1 and we set SNR to 0 at the exact same time, it can lead to a metastable state. Another case is starting with Q equals 0, a pulse on S with a duration that is approximately equal to a propagation delay in Q. So if that duration of the pulse is exactly the same or approximately the same as that epsilon, that propagation delay in Q, then it's metastable and its behavior is unpredictable. You can also think of metastable as whatever input state can lead to unpredictability in the output. But the two that I care about you knowing about are these two: a simultaneous switch from 0 to 1 in SNR, and starting with Q equals 0, a pulse on S with a duration that is approximately equal to the propagation delay in Q. Right? A test question might be, which of the following is a case that can lead to a metastable state, right? And one of these is here. Any questions about metastability? Any input state that leads to unpredictable output? Jared asks, is it 0 to 1 or 1 to 0? Is what 0 to 1 or 1 to 0? Oh, did I say 0 to 1 here? Yeah, so it should be 1 to 0. The one that we saw a couple slides ago. Oh man, that is unrelated. Can you do a digital version of an op amp? Yes, but maybe not in the not quite in the way that you would think about it. Man, that's like a whole course to answer that question. Yeah, that's a deep dive question we don't have time for today. It's a good question though. Yeah, there's a whole lot of worms in that can. The answer is maybe, probably, but it would be pretty complex and sophisticated. It might not be as cut and dry as you might think it is. Okay, let's keep it going. So next thing we need to talk about is deriving the characteristic equation. So we need to make sure we have definitions for present state versus next state. And our definitions are this. Present state is the state of Q output of the latch or flip-flop at the time any input signal changes. So when we change our input signal, whatever the output state, whatever Q is, right, that's our present state. The next state is the state of the Q output after the latch or flip-flop has reacted to the input change and stabilized. That's important, and stabilized. So once we change the input, stuff happens, things get triggered, and then its Q is going to be in some state, and then once it finally stabilizes, once it reaches a place of stability, that's our next state, whatever it's going to end up in. There might be some, all kinds of things happening, right? It might trigger a couple times before it reaches stability, but whenever it finally reaches its stable state, that's our next state. So present state is whatever Q is when we change our input, and next state is whatever it ends up as. So from there, let's talk about the characteristic equation. The characteristic equation is also called the next state equation, an equation that expresses the next state of a latch in terms of its present state and its input. So let's use this for example. So we have S and R, and we have Q and P as our output. So we're going to derive characteristic equations or next state equations for Q and for P. So we'll kind of keep that there right next to us. So to start off, we'll simplify it a little bit here in a second, but let's start off by just remembering that everything happens in terms of time, right? So over time, things are changing. So let's say Q as a function of time represents the present state, and we'll say Q as a function of time plus that propagation delay, so Q of T plus epsilon represents the next state. Make sure we got that. Now, if we were to go and do the Boolean algebra, we'll see that Q, the next state, is equal to R of T prime and S of T or Q of T. Remember, this is still a Boolean, even though we've done these as functions of time, it's still a Boolean expression, right? It's R prime and S prime or Q prime. And of course, using the distributive property, we can say Q is equal to R prime and S or R prime, and q. And if you were to work this out as a Boolean expression, you would sort of get the exact same thing. You got to do some De Morgan's theorem to deal with the NOR gate. But after you sort of hash that out, this is the expression that you would get for q. We can also write an output equation for p. And that one's pretty easy. That one is just s prime and q prime, right? Since it comes back around. And that's just directly De Morgan's theorem, right? S or q prime, would be s prime and q prime. So that's pretty simple. And so if we put them all together, we can simplify just a little bit. Instead of writing everything in terms of t and epsilon, we're going to just call q as the present state and q plus to represent the next state. And we'll distill these down in a much simpler expression. So q plus is equal to r prime and s, or r prime and q, and p is equal to s prime and q. So just remember that q plus is the next state, and q is the present state. So it's almost recursive, but not quite. All right. Any questions about how we derived these two expressions? These two characteristic equations? All right. So we started with, right, we have q plus is equal to r prime s or r prime q. We can actually take it a step further, and we can simplify the characteristic equation by plotting it on a k-map. So if we took that original expression and plotted it here on a k-map, right, and had a truth table, so we have three possible inputs. We treat present state as an input, so SRQ triggers all the way down. Remember that these two inputs, S and R, both equal to 1, are inputs that aren't allowed. So those are don't care conditions. And we plot it all on a k-map with our don't cares. We can actually simplify it down to just be q plus is equal to S or R prime and q. So this is our characteristic equation for our S-R latch. The next state is equal to S or, so set or reset prime and the present state. All right, we've got a few minutes left. So we often, when we're representing our sequential circuits, we'll put it into a table that has a little bit of a different structure. It's sort of similar to a truth table, but not quite the same as a truth table. We'll have here in the left-hand column the present state, whatever Q is, right? Q could be 0 or 1. And then in this second big column, it's going to be whatever the next state is, right? So if SR together are 0, 0, right? Then if present state is Q, then next state is Q, right? If present state is 1, the next state is 1. Then if S and R are 0 and 1, so if we're in the reset state, then if present state was Q was 0, then it's 0, right? Then if present state was 1, then it's still 0, right? Because reset R equals 1 goes to 0. SR should never exist, so that's just 0, 0. And then SR, when set is 1 and reset is 0, then no matter what the present state is, they should both equal 1. And we basically get the same for, or the same structure here for our output P for the different values of S and R. The take-home message here is break it out into different things, right? So the first column will always be whatever the present state is, and then the next thing will be our next states and maybe our outputs, and we'll group them by the inputs individually. So this is the structure of a latch table. Any questions about that? All right. We've only got like a minute left. So in fact, you know what we'll do? We'll go ahead and call it right here since we're out of time. And we'll pick up here where we left off, and then we'll do the next section on Wednesday. So Michael asked a great question. Why are some of the values circled? Let me look it over one more time. You know how many miles? I actually don't know. I mean, obviously copied this out of the textbook. I don't remember exactly why some of these are circled. I originally thought it was because it was when they changed, but I'm looking at the table now and it doesn't seem to be the case. I don't know. I'll figure it out and I'll answer that for you first thing on Wednesday. All right. Any other questions about what we talked about today? All right.
If you do the experiment with the for the random number generator, you should let me know how it turns out because I'm curious now.
Yeah, I'll let you know. Maybe you can do it. You can let me know.
I don't have the gates at my house.
Ah, I got you. Get on DigiKey, man. Pick them up. All right. So, let's see. I think that is it. Yeah. So if there's nothing else, thank you so much, guys. I will see you on Wednesday, and we'll pick up with gated latches, and then we'll move into the next section. Talk about flip-flops. So have a good rest of your day, and I'll see you guys on Wednesday.